Okay, for today's lesson we're going to revisit the notion of a limit that we studied in Chapter 2 of AB Calculus. So we're dealing with Section 9.2 here, which we call L'Hopital's rule. And we're going to revisit some of the things that we learned about limits in the past, and then we're going to enhance those and learn some new techniques to deal with finding limits at points and also limits at infinity or negative infinity. So we're going to start with a particular type of what we call an indeterminate form. And when we deal with an indeterminate form, we have several that we're going to encounter. And the first one is going to be of the form 0 over 0. Okay? What it boils down to is if we have something that's 0 on top and 0 on the bottom, we call that an indeterminate form. If we had something like 5 over 0, we would know that that would simply be undefined. If we had 0 on top and some other number on the bottom, then that would be 0. But when we have a situation that leads us to a 0 over 0, and that's what we call, again, an indeterminate form. So something needs to be done in order for us to determine whether or not there's a limit at a particular point, or also at infinity or negative infinity. So let's take a look at an example of a function that we know how to deal with from our previous work. And if I ask you for the limit as x approaches 3 of x minus 3 over x squared minus 9. Okay? So we have a couple different options here. When we first looked at limits, one of the things that we try to do is a direct evaluation, and what it boils down to is we can recognize that this is a L'Hopital's rule problem, because when we try to do the direct evaluation and we put 3 into both of the x positions, we're going to get 0 on the top, we're going to get 0 on the bottom. That makes it ultimately indeterminate. So in the end here, we're going to use L'Hopital's rule to figure out the answer to this, but before we do that, we're going to do it with some techniques that we learned in AB calculus. So one of the techniques that we looked at was using a calculator to graph, and we could see what the limit might be as we approach 3 from both sides and see if we do in fact have a limit. And we already know that this type of function is going to be a situation where we have a hole, otherwise there would be no limit. So if we just get our standard window here and we look at x equals 3 and we say we zoom in on that 3 area, we'll move her over to 3 and we'll hit enter here. If we look at our zoom, and remember, in your graphing calculator, you're not going to be able to see a hole. However, if you did your table, put your table set on auto, and look at your table. Let's go back and start at 0. All right, here we are. And then we can see there at 3 we have an error. And around 3, between 2 and 4, we can see that the answers here on the left and right of 3 are similar to one another. If we made the scale a little bit less, like 0.01, if you will, and say we start at 3, so we go right at the hole itself, and we can see that on either side the answers are virtually the same. And again, we could get more accurate with that, but we can see that that is in fact the case. So the question is, what next? Well, we know that at that point we could see that the answer here is going to be approximately 0.166 or 167, which we know is 1/6 as a fraction, and that would just give us an idea of what the limit would be like at that point. So we can make an estimate from the graph or table. Now, we also learned in our work previous to this, in AB calculus, that we could, if we can't directly evaluate it, and we can see that there is in fact a limit here, because on the left and right we're approaching the same value, that we could try some algebra and see if there's anything algebraically we do with that. So we can see that this clearly is factorable, and we learned this in pre-calc and advanced algebra for that matter too, that if we factor the top or bottom or both, and we see that there's a factor that cancels out, that this factor in fact produces a hole in the graph instead of an asymptote. And you'll notice when we first graphed it, there was an asymptote at -3 because this is a non-removable discontinuity. This, remember from our previous work, is a removable discontinuity. So at x equals 3, we know that in the graph there's a hole. Right? So the question is, how do we fill the hole, or what would the y value of the hole be if there wasn't a hole there, etc.? Well, we just changed our function now to the limit as x approaches 3 of 1 over x plus 3, because we know that these two functions are going to behave exactly the same as one another, only this one's going to have a hole, this one is not. And now, notice what we can do. We can take and we can directly evaluate. And if we put a 3 in there, we're going to get 1 over 6, which matches up with that 0.167 that we saw in the calculator. So that was what we would have done in the past for that type of problem in order to figure out that limit. And those are all good techniques. The only problem with them though is that they don't always work. We're not always able to factor the argument that we're dealing with, and therefore we need something else. We need something a little bit stronger. So that brings us to L'Hopital's rule. So here's what L'Hopital's rule states. The bottom line is if we have a 0 over 0 situation, and with our f of x over g of x, whatever two functions that we have, if they give us 0 over 0, then what we can do then next is we can take the derivative of f and the derivative of g and then reevaluate. Okay? So let's see how that would work in this problem. So if we took the derivative of the top function here, we get 1. If we took the derivative of the bottom function, we get 2x. Okay? And the question is now what happens if we try to directly evaluate? Well, we get 1 over 3 times 2, which is 1/6. And with L'Hopital's rule, we can get to the same result that we got with the algebra that we learned in pre-calc, etc. Okay? So, is one of these ways better than the other? Not necessarily. This just gives us an opportunity to do it another way, still show that algebraically we get the same answer. Okay? Like I said earlier too, the one nice thing about this particular situation is that even though we can do this with the previously learned information, okay, we can do it very nicely with L'Hopital's rule, and L'Hopital's rule is going to work very nicely for other functions besides this where we may or may not be able to do that said algebra. Okay? So taking a look at another problem, here is an example using L'Hopital's rule. If we had something like, let's say, limit as x approaches 2 of 2 plus x minus 2 all over x minus 2. So this being our argument this time, and we see if we put a 2 in there, we're going to get 4, radical 4 on top minus 2, that's 0. And then 2 in here is 2 minus 2, which is 0 again. So we do get a 0 over 0 situation. So we're not able to directly evaluate that. There actually is some algebra we can do, and you may remember it from our AB work, but bottom line is here, let's just use L'Hopital's rule this time and see if we can come up with an answer for it. So we know that this, if we do the derivative of this, this is 2 plus x to the 1/2, so that's going to be 1/2, 2 plus x, that is, 2 plus x to the negative 1/2, and the minus 2, of course, is going to be 0. And then at the bottom, we're going to have just a 1 because x minus 2's derivative is 0. So notice we're not using the quotient rule here. Be careful not to confuse it with that. And the L'Hopital's rule is just the derivative of the top over the derivative of the bottom. Okay? And then the key issue, once we do that technique, are we able to put a 2 in there and get a valid answer here, get something that makes sense? So if we were to put our 2 into here, we'd get 4 in the parentheses. And we know that 4 to the negative 1/2 is really 1 over 4 to the 1/2, which is that. And if we do the math on that, we're going to wind up with a quarter. On the screen here. So again, 4 to the negative 1/2 is 1 over 4 to the 1/2, which is the square root of 4. And so we get a half here and a half here, we'd make a quarter. Then again, we can verify that by tables, etc. And again, there's an algebra way to do that one, but we'll not do that here. So that's L'Hopital's rule in a nutshell here. But one thing that we're going to see also when dealing with this particular rule is that if we take a function like this one perhaps, and we go limit as x approaches 0 of 1 plus cosine x over x squared, and we are asked to do that one, okay, then if we would put a 0 into these, we would get that 0 over 0. And I will continue this in part 2.